Thanks a lot, Mark, and thanks a lot to Simon for letting me along, and also for Alvaro for so today I'm going to be talking about physics-based audio. So I'll talk about both sound synthesis and virtual acoustics. And what I'll do is I'll start by just giving you a kind of a general historical overview of where things have been, where things are going. And then I'll take you through a bunch of representative examples of the kinds of systems you can deal with in this way. And then, to realize our engineers, I'll go into some of the slightly more technical details about how these synthesis and effects out of them work. Some of the strengths, some of the weaknesses, some maybe points of comparison with things you may be working on in machine learning world. And then finally, I'll round things out with some useful examples. So some that were generated offline on sort of large hardware, and then some new, more recent developments in real-time buckets. Okay, so before I get going, just a word about our group up in Edinburgh. So we're much smaller, of course, than C4DM. And we have a sort of a slightly different kind of history. I mean, we're in a slightly different orbit, I guess I would say, than Queen Mary, because we're a little more focused on acoustics. So we came out of the School of Physics and Astronomy back in the 60s, where people were interested in experimental and musical acoustics, trying to figure out how these instruments work. And since then, we've sort of gone digital, I would say, and migrated over to the School of Music, which is part of the Edinburgh College of Art, which is one of the units within the university. And we've grown a bit over the last few years. So we work on mostly topics in experimental computational acoustics, but also audio signal processing, and also music tech. So there are now 5 of us, permanent staff in the group. And we work on a lot of different aspects of acoustics, audio signal processing, and we have a new appointment about to start in January on machine learning, so hopefully they'll wake up with machine learning at some point in the future. But alongside these kind of more technical folks, there's also an artistic dimension too. So we have composers, sound designers, game audio people, and also people with recording production that we work very closely with. So together we run 2 MSc programs, the MSc in Acoustics and Music Tech, which some of you may have even been through, like if I don't see any familiar faces here, but some certainly have gone on to Queen Mary for PhD studies. And then the MSc in Sound Design, which has gotten very big now. And then we run, as of a few years ago, a new undergraduate degree in BSc in Acoustics and Music Tech. And the main people we work with up in Edinburgh are something called the Center for Design Informatics, which is kind of a big kind of arts-based computing center almost. And then also with the parallel computing centers, we have a long relationship, particularly with some of the stuff I'm going to show you today on trying to get codes running on GPUs. And then externally, the main groups that we work with are Aalto University in Finland and also here now. Okay, so let me just start out by giving a little bit of an overview of what physics-based audio is. So the idea is, it's actually very straightforward. We're just trying to obtain the highest quality, natural sounding, synthetic sound we can get through the use of simulation. And there are sort of 2 main branches to the kind of work that goes on in this area. So first of all, there's synthesis. So here we're talking about producing sound from scratch, so without any kind of audio input or samples. And that could be either for familiar musical instrument or system, something like, say, this trumpet that I have a video of here, or it could be something imaginary, which somehow obeys the laws of physics. And so we hope that by sticking to physical principles, we'll be able to get sound that has that natural acoustic character that acoustic sound does, but is somehow new and allows musicians access to new timbres that somehow have kind of a footing in the real world. So that's synthesis, but beyond synthesis, there's also effects. And so the big one, at least for us, is virtual acoustics. So here now we are talking about something that has audio in. So we're taking a sound and we're using physics to describe the system that processes the audio. So on the left here we have a big simulation of a concert hall. This is the Musikverein in Vienna, I think. And so that's one example. Another example is this emulation of a spring reverb we have here at Reid. So this is a mechanical system where you drive the spring at one end with an audio signal and then read it out at the other, and you have a kind of a characteristic reverberant sound. Okay, so one thing I won't talk about today is, unfortunately, is virtual analog electronics, which is very closely allied to everything I'm going to talk about today. Sort of the white box approach to doing the emulation of circuits that you find in, say, amps or pedals or something like that. So there wasn't space. I'd love to talk about it. Okay, so how about physics-based audio versus something closer to what you guys do in AIM? So data sort of centered approaches, I guess you might call them. A distinguishing feature of physics-based audio is it's completely algorithmic. So no samples are used at all. So it's, everything is just generated from scratch. And this has a lot of implications for what you end up with in terms of an algorithm. So first of all, the codes are tiny. So generally, if you are working on a physical modeling code and you need to, say, ship it to someone to turn it into a plugin, it's very small. So it's on the order of about 10 to 20 kilobytes normally. So there are no big tables of data that accompany it. Everything is just kind of encoded in the algorithm. However, this doesn't mean that they're cheap to run. So the computational and memory costs can be small or very large, like depending on the system you're looking at. So for typical musical systems, things like strings, acoustic tubes are pretty small these days. But for something like a room, it can get really enormous. And the parameter sets are also very small. So if you think about something like a string, in order to completely characterize it, all you need to know are the length of it, the radius, the tension applied to it, and then something about the material, say density of the material or Young's modulus or something like that. So about 5 numbers, maybe a few more, like depending on how deeply you want to go into the model, but not many. So one of the real challenges for us though is trying to get these numbers because sometimes they're not readily available. Some of them are easy to get, like the length of a string is pretty simple, the radius as well, but figuring out the tension is harder. And then even something like the density, like if you think about a real string, like it's not just a solid piece of nylon, or well, if it's nylon it's easy, but if it's something like a bound guitar string, it might require some work to figure out what the actual density is. And so this is kind of the strict viewpoint, like in terms of simulation. Like when people make commercial products based on physical modeling, like often they extend this to include samples for the sounds that are hard to model. So a good example of something like this might be a key click that you'd have on say a wind instrument. So that, I mean, it's a relatively simple sound, but it would be a lot of work to try to go and model that sort of collision of a piece of metal with a piece of metal. So people tend to avoid that kind of complicated modeling for sounds that are relatively simple, and you just go and sample it. Now in terms of operation, these always work as recursions at an audio sample rate. So you can think about them as big feedback or IR systems. Okay, now what about procedural audio? So I'm just mentioning this because there was a great review article that just came out by, I think, Josh and his students about a week ago in a peer research gave, kind of laying out sort of the whole domain of procedural audio. So procedural audio is also algorithmic. I guess it kind of has different origins. It came out of the world of game audio, sound effects. And I think the idea there is to try to not do full sort of physical modeling of systems, but rather try to extract what's perceptually important from them in order to be able to cope with sounds that might be harder to deal with in simulation. So if you think about something like, say, footsteps, or what else, like helicopter sounds or something, like that would be something that would be pretty hard to deal with a full physical model. So you want to try to simplify that down. So I find it useful sometimes to think about, like, if you're trying to figure out like what type of modeling you're doing, believe it or not, sometimes like you're not actually sure. It's useful to think about whether you are solving some set of equations, and this for me would be the kind of the strict viewpoint of what physics-based audio is, or are you making use of solutions in order to generate the sound? So in this case, we've got, say, the simple harmonic oscillator, and we could view that as an equation that we could go solve on a computer. In this case, though, I mean, we happen to know what the solution is, so we could directly bypass the stage of trying to compute this numerically, just use the solution to generate sound. And this would be the basis for something like an additive method or something, where you added together a bunch of sinusoids. However, the thing to remember is that you don't always have access to the solution. In fact, most of the time you don't, which is why you're faced with having to solve this equation rather than making use of a solution. Okay, so there's no training in this methodology at all. And it's the mathematical model and not the sound it generates that is the ground truth, really. And so I really don't want to get into talking about machine learning approaches to audio because you guys know way more about it than I do. But I think it is true that usually it's the audio that's the ground truth. And I mean, however, I'm sure these days you're incorporating all sorts of things about the physics of whatever system you're looking at in order to, say, refine, say, a machine learning approach to generating sound. Okay, so today I'm just going to talk about strict kind of equation-based approaches to physical modeling. Okay, so what are these classic approaches? Okay, they go back quite a ways. The very first attempts at speech synthesis, in fact, were exactly physical models. So if you think about the Kelly-Lochbaum vocal tract model, that was designed as an emulation of the vocal tract, wave propagation in the vocal tract, if it's assumed to be broken down into a set of concatenated acoustic tubes. So it's precisely that. A little bit later, there was some very early attempt at kind of a brute force simulation of the string. So this came out in the Audio Engineering Society Journal in '71, based on some work by a master student about a year earlier. And at that point, like, computers were really not up to the task of trying to do this, and this whole direction dropped for about 25 to 30 years until computers kind of caught up. So what you saw in the meantime were systems that were developed to be used by musicians. So one of the first was came out of Grenoble, and it's based on a mass spring network formalism. So a composer would go or a musician would go and build their own instrument out of a bunch of kind of canonical objects. So masses, springs, connect them however they wanted, and then listen to the sound. And then you see progressively more kind of complicated systems emerging over the 1980s. So modal synthesis came out of IRCAM. So here you break down the motion of a complicated dynamics of an object in the modes, and each mode oscillates at its own natural frequency, and you kind of build up sound partial by partial. But I guess the big breakthrough was probably digital waveguides, which came out of Karma at Stanford in the 1980s. And this was really quite something because it was so efficient that it allowed real-time audio for string models and acoustic tube models in the late 80s and early 90s, just on commercial hardware. So the thing about these methods is they were all, their computational constraints were so severe at that time, so that people really had to make a lot of simplifications in order to get these to run. And things kind of opened up a bit, like after a little pause, sort of in the 1990s, when musical acoustics investigators began to try to look at the dynamics of more complicated instruments. such as, for example, a timpani drum. This was kind of the paper that really got me interested in this field, this paper by Reid, and Jolie from 1999, where they really did a full model of a timpani drum, including everything. So the membrane, acoustic field, everything you can imagine here, the mallet. And they were going back to this approach of doing brute force simulation on this big coupled system, including the acoustic field, which turns out to be really important for any kind of drum modeling. You really can't do without it. And as you might imagine, this was a pretty big computation. So this is offline back then, way offline. Okay, so before I get into the example systems that I'm going to look at in the next few slides, I just wanted to sort of show you some of the different ways in which different system families, I guess, that have been looked at over the past little while. So the first one really is the classic model of a musical instrument represented in terms of an excitation mechanism. So in this case here, I have a bowing excitation, which is strongly nonlinear, but modeled as kind of point-like. And then a resonator, which is assumed to occupy space. And so this is the classic model. It applies to the case of wind instruments too, where the excitation would be a lip-reed interaction. Also to the hammer-string interaction. So it applies kind of generally to a lot of different instrument types. But then people have sort of gone further and looked at, say, modular instrument constructions, where you might take a bunch of canonical elements. So in this case, maybe something like a metal plate, connect them all together, and then build your own instrument. So this doesn't really have a referent in the real world. Then there are multiphysics problems. So here we're coupling together different components of a consolidated system, but the components are all different. So in this case, the case of the drum, we have the acoustic field, membrane, cavity, and also the mallet, all kind of interacting with one another. And then there are systems that just have an inherent complexity all their own. So even if they're maybe just a single component, within that there's a lot of algebraic complexity in there that's required in order to be able to emulate the sound. So a good example is something like, say, a gong or a cymbal. Another good example is a spring reverb, which is an enormously complicated linear system. Okay, so let me start showing you around now some of the sound types that you can emulate this way. So first of all, let's start with wind instruments. So here we have a generally coupled set of acoustic tubes. So there's something called the main bore, which is a tube of variable cross-section that goes from your lips all the way to the bell. And depending on the type of instrument, you may have valves, so introducing new sort of bypass tubing segments, or you might have a slide in the case of a trombone, or in a woodwind instrument you might have additional holes, tone holes, used in order to change the effective length of the main tube. And this kind of thing is actually easily real-time these days. It has been for a while. Even for long instruments. The longest is the trombone, which is about 4 meters if you completely extend the slide. And it's really interesting because when you design one of these methods and you first start messing around with it, the sounds you get out are very similar to the sounds you would get out if you were, say, a kid, like learning how to play one of these instruments. I'll just play you a typical first sound you get out. So you get this kind of not very steady sound. And really what you need to do as a musician is go and learn how to kind of harness this or tame it. And that you do that not with your lips, but by like figuring out the right set of numbers that you need to apply in order to try to stabilize this. So we do this manually, but it's obviously something that would be a really great thing to be able to do automatically in a smarter way, So eventually you can sort of play say up the harmonic series. And then, when you get even better, you can sort of play around with the gestures a little more. So at this point, you know, I'm just an engineer, so I'm not a musician. So the thing to do is to immediately pass this over to a musician to try to get the most out of it. And so that's what we did. We gave it to one of our colleagues up at Edinburgh, Tom Mudd. He went and did an album, actually, based on this. This is just a short sample. So he was kind of got in there and started building his own instrument because he wanted to not just, you know, produce standard wind instrument sounds. He wanted to see how far he could push it. So he's getting this kind of stuff. Okay, so let me move over to a different system now. So guitars. These are also, these are more complicated actually to deal with than wind instruments, just because of the variety of the different components that make it up. So first of all, you have the strings, so the primary vibrating component. But the real complication here is the presence of the sort of backboard or the fretboard, and in particular the frets, the sort of raised bumps along the fretboard that allow you sort of a quantification of the pitch. And on top of that, you've got the fingers, which you need to really model like in their entirety as little masses that are in contact with the strings, and also potentially leading to these triple contacts between the finger, the string, and the fretboard. So you need to model all of these together, really. And then you've got the body and the acoustic field, which I mean, you need the acoustic field in order to hear it. So this also is real time if you give up on modeling the body and the acoustic field part, so the radiation. And you can, even still, you can get pretty good approximations to the sound of a guitar. So here's sort of basic, you know, playing up the strings. But what you can do is, again, just like in the case of wind instruments, you can get in there and try to learn through sets of control data what kind of input you need to apply in terms of computers in order to be able to generate, say, familiar gestures, like, say, barring chords, for example. Here's one example. So in that example, I mean, that's a strumming, but then with a bar, but what you also hear is a kind of sort of rattly noisiness there, and that's because of this partial intermittent contact of the strings with the fret. If you have an imperfect contact, you're going to get that, and that's what the physical model is able to give you. This one, and then you can also do stuff like play on the harmonics. That's basically a bar chord, but with variable force applied to it. So sometimes it's very light, allowing for a more rattly timbre and also activating some of the higher harmonics of the strings. And you know, just like before, like the thing to do at this point is to pass it over to a musician. So we gave this to another musician, Milan-based composer named Gadi Sassoon, and he did another album, came out a couple of years ago. And he, again, like Tom Mudd up in Edinburgh, was interested in trying to, he didn't really care about emulating guitar sounds from the real world. He wanted to go build his own. So he did that, spent a long time designing it, and then finally got around to playing it. Okay, so at this point, let me sort of sidestep into the world of virtual acoustics and talk a bit about room modeling. I'll come back to musical instruments in a second, but I wanted to just show you a bit about rooms. So the industry standard, if you go out and you want to, you're an architect and you want to try to audition like what your room is going to sound like before you build it. There are packages out there to do this. So Odeon is one, CAT is another. And for the most part, they're based on geometrical acoustics, so this approximation of particles or rays. Right? So you imagine a source is emanating waves in all directions, and then these bounce around the space, and then are collected at some receiver. It could be like a microphone or your ear or something. And this is it's a good first approximation. It's not complete though, because it neglects the effects of diffraction. And just to illustrate that, consider the case of two coupled rooms, and a source in one of them. And you immediately see that the ray picture is not really going to capture effects like the bending of waves around this opening between the two rooms. So in order to deal with this, you need to move to a full kind of wave-based picture of wave propagation in spaces. And this is really complete, actually, in terms of the physics. So what you're doing is you're solving the wave equation over a big enclosure. And you could do this amazingly for relatively large spaces and even up at an audio rate. So this is something we worked a lot on, like actually for the past about 10 years or so. And you can kind of get to the stage where you could put in like a building schematic, and if you know something about what the materials are on the surfaces of the walls, on the wall surfaces, then you can get a pretty good emulation of the IR for the room. So here's one example. So this is computed at, I think, 50 kilohertz, and it was for a pretty large space, actually. So this is on the order of, I think, 4,000 to 5,000 cubic meters. So here's an audio sample going in. This is dry. And then here's processed. So the big job here really has to do more with the walls. So that's like a lot of our kind of effort has gone into figuring out exactly how to emulate kind of the complex frequency-dependent reflectance of wall materials, because it really matters for the resulting sound. At audio rates, this turns out to be pretty heavy, very heavy computationally actually, and the reason is kind of a fundamental one. So in order to be able to emulate this entirety of the acoustic field in a space like this, you need to be able to get it. You need to have a resolution which captures the shortest possible wavelength you can hear, which is about this, right? So you can imagine, I don't know, filling this room or something with this spacing, and it's going to amount to quite a lot of memory that you need to operate on. And then on top of that, you're operating at an audio sample rate, so 50,000 times per second. So it gets big. But you can still kind of just about do it, like in a big enough room, if you have, a set of GPUs, you can just about fit that into memory and run that. And that's what we did here, actually. Okay, so now let's sort of circle back to musical instruments, and in particular to percussion instruments, where you do need to model 3D wave propagation if you want to get the sound of it properly, actually. So here are a couple of examples, actually. So think about, say, a set of gongs, right? So this is a kind of an instrument setup that we came up with a while back. So these are sheets of metal, like embedded together in an acoustic space. And one of the nice things about working with 3D like this is you immediately have access to multi-channel output. So you can go take outputs wherever you want around the system, and you immediately have spatialization for this. So I'll just play you some sort of gong-like outputs. So these are. And then you can also do the same thing with drums. So these are now timpanis, all in the same space. And I'll just play the sound. And the kind of interesting thing here is that if you have several of these in one space, like if you excite one of them, it'll excite the acoustic field, but it'll also set the others in motion. So even if you haven't struck them directly, they'll all start moving together, just because of the field interactions. Okay, so I thought it'd be interesting to just deconstruct one particular instrument to show you the effects of the different layers of approximation you go through if you were going to try to build it. So let's take the case of the snare drum. So the simplest thing you might try to do would be just to model this as a pure membrane. So just kind of floating there in a vacuum, so there's no acoustic field around it. So you can imagine this is just a taut membrane almost in outer space or something. And if you were to put a contact mic on it, the sound you get out is really doesn't sound much like a drum at all. See, there's a kind of tonal component there. So those are the modes of the circular membrane that you're hearing there that's giving it that kind of pitched sound. But it's quite far, right, from a drum. Now, suppose you add in the snares. So this has a big effect on the sound. So the snares on the snare drum are on the bottom membrane, and they're sort of affixed against the snare drum, so it's such that when you hit the top membrane, it excites the acoustic field in the interior, sets the bottom membrane in motion, and then that introduces this kind of intermittent contact with these wires that are stretched against it. And it gives you like a noise-like timbre. And here's that. But even that isn't really complete. So here's where the 3D comes in. So once you put this into a cavity, or once you model the cavity between two of these membranes, you get something called the so-called cavity modes. And this is what sort of gives the snare drum this kind of pitched sound. All right? And then finally, you could go and put these in a larger space if you wanted to capture this in capture the room effects as well. So here are two of these drums now in a large room. Okay. So far, most of what I've shown here today these have been emulations of instruments that exist in the real world or acoustic spaces that house them. But one of the real interests of physical modeling is trying to allow musicians access to new sounds, so allow them to build their own instruments. And one thing we worked on quite a lot up in Edinburgh is toolboxes for sort of modular construction of instruments, where the musician can sit down and say, okay, give me a set of plates, give me some way to connect them, and then I will spend some time learning how to play this. And we have several of these sort of setups at the moment. This is one of the first, actually. This goes back to 2009. And we had one composer, Gordon Delap from Maynooth in Ireland, came over and spent a long time actually building this thing and learning how to play it. So he spent probably about a month actually constructing the thing. It was made up of hundreds of components, and then eventually just sent in one big score into a single unified instrument, and this piece based on it. Electromechanical reverbs, because I know you guys also working on, I think, spring reverbs at the moment. And this is a really good candidate for physics-based approach. So spring reverbs, I said a bit about them earlier. Like normally you have a few of them within a single unit. In each case you have a kind of magnetic driver at one end, and then you have a pickup at the other end. And it's surprisingly messy, actually, the physics of springs. Like, I wouldn't have thought prior to looking at this system that it would makes such a difference to have a, you know, a piece of metal wound in a coil compared with a piece of metal in a straight, like just in a straight line, but it does have a huge effect on the resulting sound. And this is something that you can also do, I think, in real time these days. So you can get pretty decent IRs this way. Reverb IR. Okay, so that's it for the systems. Now I want to go through some of the details about how these work. And let's just go right to the runtime loop. So if you have a piece of code running at an audio array, what does the runtime loop look like? Well, it's surprisingly simple. And just to see the very simplest case, let's take a look at a linear system. This is very unrealistic, right? For virtually all interesting systems with some kind of nonlinearity in them. But for a linear system, any physical modeling synthesis method is going to look like a state space form. So it'll have this rough structure. So we have a loop running over all the time steps. We have a first line, which is an update. So it maps our previous state, whatever that is, to the next state, and accepts an input. So the state, by the way, is some vector. And that just includes everything we need in order to, all the dependent variables that we need to describe the system. So for something like an acoustic tube, it could be a set of pressures at a bunch of points along the tube. For a string, it could be displacements at all the points along the string. For a room, it would be a collection of the pressures at all the points in the room in which you are modeling them. And then the second line is where we draw outputs. And then finally, there's a stage where we shift everything back again in sort of preparation for a reset here. And a key parameter here then is how big is this state size, right? And that we might call our number of degrees of freedom for the system, or N. And this is going to determine the computational cost. And this varies a lot, like depending on what type of system you're looking at. The other thing that's interesting is that this system, which is described by these matrices here, I mean, it's not actually a general system. Like the state matrix here, A, is actually normally very sparse in simulation. And that reflects the kind of locality of the dynamics, right? So normally, like if you have an excitation at one point on an object, it's only in the sort of local region around that you're going to expect to see some kind of effect. And that locality is reflected in the sparsity of these system matrices. And that's good. That's a real win, right, in terms of both storage and operation count as well. So now let's take a look at the slightly more general, or much more general actually, nonlinear case, right? So in that case, in general, like if we come up with a numerical method for simulation, we won't have this kind of explicit update. What we have is a big system of nonlinear algebraic equations that we need to solve at each time step. And that's really bad because that's expensive to do. It's going to require some kind of iterative method. And remember that this is potentially a large vector that we need to solve for. So the state size can be big. It can go up to, you know, 1 million for a room. It can go up to, you know, hundreds of thousands for a base drug membrane or something. So this is really something we are trying to avoid, and that's been kind of a main sort of focus of our work up in Edinburgh over the last few years, is trying to simplify this as much as possible and arrive at explicit updates. So we can never remove the nonlinearity, but we'd like to have it in a form such that we can update the next set of states explicitly through a nonlinear function applied to the last set of values of the state, but without having to do any kind of iterative solution. So this has really allowed us to move a lot of systems into real time. I mean, you can sort of interpret this actually as a large kind of nonlinear IIR filtering operation, or I think what's called a NARCS system, right? Nonlinear autoregressive system. So we have our state, we're applying some kind of nonlinear function to it, and then resetting the state in terms of that. Okay, so in terms of problem size, let's go back to that number of degrees of freedom that we require. So this is highly system dependent. So if we're operating at, say, 44.1, what I've got here is kind of ranges for the numbers of degrees of freedom you need in order to, or the state sizes you need. And these actually follow directly from the parameters that define the system. So if you go back to that example of the string and think about, you know, the length and the tension and all those parameters, you can use those to arrive at this number, which is kind of like a price tag for a particular instrument. So if you look at the case of a string, like for most musical strings, this number of degrees of freedom is in the order of somewhere between 50 and about 200. And that's pretty reasonable for anything in real time. For acoustic tubes, it's a bit bigger, just because the tubes could be long, like is in the case of the trombone, say. And then as you move to higher dimensional systems, so something like a plate or membrane, then they get bigger. So for plates, so generally stiff plates are cheaper than dealing with membranes. For stiff plates, you can get away with sort of state sizes on the order of about 1,000 or so. And then for big bass drum membranes, you can get up to roughly about 100,000 for the largest cases of interest. And then there's kind of a big gap, and then you have rooms where state sizes get very big, so up into the billions. So just for context, these days, so when we turn something into a plug-in, we know that we can deal with about 4,000 to 5,000 degrees of freedom comfortably. So if we want to have a plug-in that operates at about 20% CPU. So this is good. So this covers tubes, strings, and then plates as well. And then we're sort of moving into drum territory now. But I mean, rooms you can see are still kind of a ways away. Okay. So I mentioned we were looking at nonlinear feedback systems, and you can imagine that stability is going to be a big problem in simulation. And the reason it's problematic with musical instruments is that, first of all, most musical systems are relatively low loss, so they tend to ring for a long time. So the dissipation is small. And also the durations of the simulations can be very long, right? So if you have I don't know, like a room simulation or something like that can have an IR that is 5 to 10 seconds. A grand piano could be close to a minute. And then if you have a plug-in, which someone just wants to keep playing all night, like that has to run for hours, and it has to run without breaking, right? And here's how they break. So here's an example of a badly designed algorithm becoming unstable here. So this is for a membrane. And you always see the same kind of thing. So you see kind of an explosive growth of the shortest wavelengths that can be represented over a grid. So it's sort of something like what happens at the Nyquist, if you're thinking about it spatially. But it also crops up in more subtle ways. So for example, you can have a system which is well behaved over the interior, but then you see explosive behavior in a poorly chosen boundary condition. So, so it's really something that you need to kind of pay a lot of attention to in these designs, because what you don't want to do is give, I don't know, a plug-in to somebody and then it just breaks all the time, especially if it's a musician, because they'll become very frustrated quickly. And it kind of gets harder when you have multiple components, like all interacting. So the kind of solution to this has to do with energy conservation. So what you can do is look at your system, and it doesn't matter what it's made up of. So it could be, let's take for example the case of, I don't know, the timpani drum. So it's made up of several different components. So there's a membrane, there's the acoustic field, there's the cavity, and there's the mallet. And you can, for this system, you can write down an expression for the total conserved energy of the system. And what you can do is make sure that in your simulation that is maintained to machine accuracy, so down to about 16 places. And if you could do that, that is actually a guarantee of numerical stability, because you know that the system can't explode on you. And just as a more interesting example maybe, here's the case of a room simulation, where on the right we see here's the simulation progressing. On the left, we see all the different components of the energy. So we see the kinetic and potential energy, we see the energy stored at the walls, we see the accumulated energy lost due to viscothermal processes in the room. And what you see is that the energy in our simulation is now conserved to 16 places. So you see that last digit there, flickering there at the top left. And if you were to zoom in on the energy over time, what you see are variations at the level of a single bit. So it's a great debugging tool, in fact, for complex systems. Like sort of build in this measure of energy, make sure it's conserved, and then once you're happy with your algorithm, you can then comment that part of the code out. So we use it a lot for the design stage. Okay, now, nonlinear systems. So this is the kind of the biggest challenge for us, is dealing with systems that have kind of a strong inherent nonlinearity. And I'll give you an example of one of the milder forms of this. So let's just take the case of string vibration at high amplitude. So we kind of all know what this sounds like. So we take a string, pluck it lightly, we get a kind of a sort of a gentle tone, but if we pluck it hard, we may get something more like a twang. And that effect is just due to nonlinearities occurring within the string itself. So I'll just play you two examples here. So here's a string being struck under linear conditions. That's 5 successive strikes. It's at higher amplitudes, and what you hear is, because it's linear, like there's no change in the resulting sound other than a change in the amplitude. However, for the nonlinear system, you get other effects coming out. So the main effect you get, of course, is this pitch glide, right? So the pitch changes a little bit at the beginning of the sound before it decays, but you also get this kind of sort of timbral complexity, which you can see in the spectrogram here too. So there are new harmonics being generated. Now, a much more dramatic example of this is the case of plate vibration. So if you think about an instrument like a gong, cymbal, or a tam-tam, at high vibration amplitudes, you have very strong nonlinear effects. So like a cymbal crash, if you imagine that, it's very different from the sound of a cymbal being hit lightly. And we have a type of nonlinearity here that's very different from the type that you have in electronic circuits, which is maybe what a lot of people are familiar with. So if you think about a plate vibrating at low amplitudes, we have vibration, say, in the lowest mode. At higher amplitudes, we start to see like a splitting of energy. So energy moves from one mode into others, and then finally we end up with almost completely chaotic behavior. It's kind of easier to see this if you look at the case of a driven plate, right? So you take a piece of metal, and you drive it with an actuator somewhere with a sinusoidal signal of increasing amplitude over time. This is what you would see in terms of the spectrogram. So at very low amplitudes, you see the entire plate oscillating at the frequency of the driving frequency. Then you start to see harmonics appearing. So this is just like harmonic distortion that you'd see in electronic circuits. But then there's this point at which, if you drive it further, the harmonics begin to bifurcate, and then you enter this chaotic regime. And I'll just play you the sound now, so you can hear. This is synthetic too, by the way. So that last part of that sound there, that is the noise that you would have in something like a cymbal. So now let me just move on to some musical examples. So I'll just say a word about the NES and WRAM projects. These ran quite a while ago, actually, so I don't want to dwell too much on them. But this was our attempt to try to see how far we could go in terms of physical modeling synthesis. So we had a team working on, first of all, algorithm design. So beginning with a number of different target systems, ranging from, like a lot of the things that I showed here today were among the target systems that we looked at. And then we had a team that was devoted to hardware acceleration. So we write codes in, say, MATLAB or something. They would convert them into serial C code and then finally get them running in CUDA on the GPUs. And then we invited musicians over to like help us learn how to use these musically. So we invited a bunch over, and we ran some workshops and did a whole bunch of compositions and performances that were really fun. So this was really a fun project to do. There was a lot of sort of musical outputs, and I'll just play you some excerpts from 3 of them. So the very first piece we did was by Gordon DeLapp from Maynooth, and he came over for almost 6 months actually, trying to wrestle with the very first iteration of our synthesis system, where it's very kind of clunky. You have to submit jobs to the GPU through a kind of very crude web interface, and you have to go and manually type in the score and all this stuff. It's very very hard to use, but he managed to do it. He did we were very interested in multi-channel too, so all these pieces were, 8-channel, 12-channel, 32 channels. He did a 12-channel piece that was based on the use of trombones, bass drums, and this is a stereo reduction, so you don't really get the whole effect, but I'll just play you a little excerpt from it. And then here's an example of the use of the sort of 3D percussion framework. This is by Alberto Torin, who did this is more of a demo, I guess, in the piece, but he was just trying to, see what kind of sound he could get out from that. Who worked a lot with our guitar model. All of those sounds are produced offline, so you had to wait around sometimes for quite a while. Normally not too long, normally like a few minutes for a few seconds out, but sometimes for some of the big percussion sounds it could be much longer than that. However, we thought it'd be good to try to move into real time, so we formed a company up in Edinburgh called Physical Audio. And the idea is to do real-time instruments and effects. And the very first one was something called Derailleur, which is pretty simple actually. It's just a set of 5 bars with 10 connections among them. And these are nonlinear connections, so you could specify all of these. And they're kind of different modes of operation. So you can either strike this thing, sawtooth input. So you can sort of think about this as you can use it almost as an effect, right? So you could actually just pipe in whatever audio sound. So if you put in sawtooth or something, you get this. Just because of the nonlinearity, you get really interesting kind of hysteresis effects. So if you send in something with a fixed pitch, you can get these sort of warbling happening. Okay, so that was the first instrument we came up with. The second one was sort of inspired by the prepared piano. So we thought it would be sort of fun to sort of group strings in pairs and then have these kind of connection elements between them that behave like rattles. So you have control as a designer over, how heavy this rattle is, like how wide it is, and its stiffness and all that kind of stuff, where you place it on the string. So you can move those around. And then we were able to get about 25 of these running in real time, like plug-in. And that became the basis for this thing called preparation, which I have a couple of videos of this being used here. So this is... So what he was doing there is he was controlling the stiffness of the preparation kind of element, the rattle thing, like in real time with one of the knobs. So the knobs are all mapped to the different parameters for that element. So this one, for example, I think is under bowing conditions. Some interesting distortion and feedback type territory that way pretty easily. And the last example is kind of the interesting one, because what you could do is just shut off all of the dissipation mechanisms in the thing. So you could then hit a bunch of keys and then just let the thing go. And because of this energy conservation property we have built into the code, we just keep running basically forever, and the sound will just keep evolving. So if you can let this thing run for minutes, hours, and this is the kind of thing you get, actually. Just a sort of a new development has been real-time gongs. So we finally managed to get this thing sort of past the real-time threshold. We have just one gong running in a sort of first version of this plugin with stereo output. And you can either do strikes, so like this, just as in the case of derailleur, you could send in, say, some kind of input. So if you send in just a pure sinusoidal input, you can hear the nonlinear effects of the plate like pretty clearly. And just to finish off here, that's my last So one thing I just wanted to highlight is it's possible now to run actually pretty big models, like in real time these days. So by big, I mean for relatively complex systems. I sort of mentioned these sort of specialized passive designs that are we really need these in order to make sure that the thing behaves well. And that's something I sort of wonder about for the folks who work on machine learning, is actually how you, like, if you have something which has a recurrent structure, like an IR type network, how do you make sure that you are maintaining numerical stability, or is that just sort of guaranteed by construction, or I'm not sure. But for us, it was kind of difficult to try to cope with this one. And then there's some other kind of useful constraints that I've kind of mentioned, actually. So one of them has to do with state size. It's been really good for us to sort of know this, like a priori, for a given system. So you can sort of look at something, just by looking at the parameters that define it, you sort of know roughly like how much computational work it's going to cost you to get a solution. And so you can immediately actually just rule certain things out. Like if you realize it's going to be impossible in real time, you know that, like, from the outset. And then you also know if you have something a system where you should be able to do it in real time, and somehow you're not able to do it because your state size is too large, that means that you're somehow wasting cycles on something that is not audible. So it's going to be kind of a target to shoot for. Yeah, so I mean, these are still not dirt cheap, so we're not like down to the level of, like, say, procedural audio, where the stuff is really just going to run in real time with very limited CPU. And then some systems are still like heavy, like 3D is not going to happen anytime soon. But for architectural acoustics applications, it may not matter so much. Maybe you're just interested in waiting around for a while, hearing what your sounds are like. But for musical use, that's kind of hard. And I think that is actually